make the introduction here. I'm super delighted to welcome Paul Grigas. Paul is an associate professor at the University of California, Berkeley. Got promoted like a year or two ago. And we are very proud because he has been part of AI4OPT for a long time, and contributing some major results for us. I think you have to know that Paul is one of the inventors of predict and optimize, which has become an entire research area on its own. He's not going to talk about that today, but he's also very broad and working on many aspects of the intersection of OR and AI. And today he's going to talk about one of my favorite topics, which is parametric computation. So Paul, that's all you do.
Great. Thank you so much, Pascal, for the nice introduction. And thanks, everyone, for welcoming me here today. And so I'm looking forward to visiting this week and interacting with everyone. So today, I'll talk about a topic that I think and hope is of interest to all of you. So it's about parametric optimization, which is a topic that some of you may have actually worked on. And I want to present a few different results that sort of highlight some of the aspects that I think are interesting about these problems, and I think that also open up a number of interesting new research directions. And so before I get started with the talk, I want to just acknowledge, I think now more than ever, important to acknowledge that this work was generously supported by the NSF and, some connection issue here. Let's see. Here we go. Let me just put it back in full screen mode. Okay, great. So yeah, I think it's important more than ever to acknowledge that this work was supported by the NSF and in particular the AI Institute. And also I want to acknowledge my collaborators and students. So this talk is based primarily on joint work with my student Shiran Dong and also collaborator Vishal Gupta from USC and also former student Hoyan Liu. I also mentioned Weam. I won't really have time to talk about her work today, but she's also working on some related things and extensions of this work. So I also want to acknowledge her, and hopefully you'll have a chance to learn from her this week as well, since she is visiting here. I'll start with a brief sort of introduction to this topic and talk about some of the motivation and preliminary ideas. And then I'll present two main sets of results. So one is about learning methods in this context. So this will be how we can adapt learning to parametric optimization. And the method that we call it is learning the optimal solution path. And then I'll present sort of at the end a different perspective for specialized problems, in particular single parameter parametric optimization problems based on an ordinary differential equation perspective. So I anticipate to probably spend the bulk of the talk on the first part, the learning aspect, and maybe 10 minutes or so at the end on the ordinary differential equations part, and then of course some conclusions. Okay, so to motivate things, I think we all recognize that parametric optimization problems are commonplace in nearly all, maybe all applications of optimization. One thing that I think is important to emphasize in this talk is the distinction between what I call endogenous and exogenous parameters. So exogenous parameters we might think of as the demand for different products or the travel time along the edges of the network. These are usually parameters that may or may not be known at the time when you need to solve the optimization problem, but they're somehow determined in a way that is outside of the scope, usually for the most part, of the decision maker. And if they're unknown, we might predict them, and then we might think about how to integrate these predictions with optimization, and that's what a lot of my other work that Pascal mentioned is about. But today's talk is really, I think, motivated and sort of centered on what I call endogenous parameters. And so endogenous means that somehow determining the right value of the parameters is part of the decision-making process, right? So think contexts like multi-objective optimization, where we have perhaps multiple competing objectives that we care about. human-in-the-loop decision making. All right, so a human may want to review these different objectives and the performance metrics associated with each one. And there's some kind of iterative process where you show the decision maker a candidate solution and they evaluate how good it is. And they tell you, no, actually, it's not that great. We need to tweak these parameters. And so this back and forth kind of process is a human-in-the-loop decision making process. And I'm really thinking today about those sort of parameters, right? So the sort of parameters that are central to that kind of process, right? A related problem is, of course, hyperparameter selection in machine learning. In a lot of ways, that one is more automated than the human-in-the-loop decision-making process. But still, somehow we think of these parameters at a different level than the more basic parameters in machine learning, like the weights in the network or the coefficients, right? So today's talk is really motivated by these type of parameters, in fact. And I think we'll see when we get to the results, like how thinking about the parameters in this different way changes the type of results that we might want to strive for. Okay, in particular, right, in all of the above cases, I think an important and really fundamental task is to try and compute optimal solutions across all values of the parameters, right? So we really want to be able to have reliable, good, approximately optimal solutions for all values of these parameters. Okay, let me give a few concrete examples to motivate it further. So one is portfolio optimization, right? In portfolio optimization, typically there's some trade-off between return and risk. And so you want to think about how to allocate your portfolio across different assets so that you maximize some combination of return and risk, weighted by some scalars lambda1 and lambda2. And maybe you also have a third term involving regularization. You might even have other terms trying to promote sparsity or multiple risk definitions and so forth. And so the classic Markowitz portfolio optimization formulation works in this way, and it trades off between return and risk. And a decision maker will examine a Pareto frontier of possible solutions, right, and decide on an allocation based on their risk profile, right? So that's one situation that we're thinking about where we have to be able to really characterize this entire portfolio, right, this entire Pareto frontier, and to do so, we really need to be able to solve our nominal portfolio optimization problem across all values of the parameters, right? That's important to characterize the frontier. Another setting is in multi-class classification or binary classification even, where there is a trade-off between false positives and false negatives, right? Or in the ROC curve, the true positive rate and the false positive rate. This is a standard thing that we teach in undergraduate machine learning, and we visualize the trade-off with this ROC curve, right? More generally, in a multi-class classification problem, right, you might have multiple classes, and the way that you care about each class, your preferences, may not be the same across all classes, right? So we really would like to be able to play with these weights across the different classes and look at the performance and ultimately decide upon some weights on these classes that are preferable for us, right? So again, we're in a situation where we need to actually solve this problem, perhaps for multiple and really all values of these parameters. And this is true as well, not just if you think about different classes in the standard way defined by the dependent variable in classification, but also if you think about different subgroups of the population, for example, determined by other variables like race, which is really important in fairness. So again, this is another a situation like where we have a parametric optimization problem that we need to solve across all the parameters. Finally, I'll mention one kind of real application in a way that I have worked on, which is about capstone team matching. So this is a problem that we solved with the Fung Institute at Berkeley, which is the part of the engineering college that's responsible for managing the Master of Engineering program. And they have a problem of, and specifically they're really doing all the legwork in managing the capstone project experience, which is a team project that the students participate in throughout the entire 2-semester program. And so they have a problem where they have hundreds of MEng students that need to be matched with a potential project run by different advisors. And there are multiple stakeholders here, the advisors, the students, the Fung Institute itself, and each of them might have different goals. So there's really an opportunity to apply optimization here, but it's not so simple as just having a single optimization problem that is clear from the start. Rather, we need to, have an iterative decision-making process, which is supported by a decision support tool that can help these decision makers visualize trade-offs and view the different outcomes and so forth. And so that's the kind of tool that we have built for them and that we're working on with them. And the kind of optimization problem that we solve then, under the hood in this tool is a parametric optimization problem defined, for example, for these 6 parameters that trade off these different criteria, like the number of matches, the quality of the matches, the number of projects running, the number of unique advisors, and so forth. So again, it's a situation where we're going to need to solve many instances of these parametric optimization problem, and really to properly understand the entire portfolio of solutions, we should solve it for all values of the parameters. Okay, so these are sort of 3 concrete examples. In general, we might have a problem that looks like this. And by the way, feel free to interrupt me at any time if you have questions. So in general, we'll have a situation like this, where we have a parametric optimization problem with decision variables theta and parameters lambda. And we call theta star of lambda the optimal solution, which is a function of the parameters lambda, where h of theta comma lambda is the objective function described by parameters lambda, right? Here, lambda is assumed to live in some parameter set capital lambda, which for most of this talk will be very arbitrary. So it can be an arbitrary set of vectors of different parameters lambda, and we don't need to assume very much about the structure of this set for most of the talk. Of course, in general, the dependence on the parameters is not just in the objective function, right? We often also have dependence of the parameters in the constraints. This talk will focus on the unconstrained case, so that's where we have our initial results. Of course, one could impose constraints in a soft way using a penalty formulation, ideas of self-supervised learning and things like that. But for simplicity in this talk, let's just assume we have an unconstrained problem, and I think extending it to constrained problems in other ways is also a very interesting future direction. Okay, so this is my problem of interest for this talk. And my goal is to efficiently compute the optimal solution here, theta star of lambda, for all lambda, right? So I want to compute this entire mapping, right? I don't just want to solve a single problem. I want to compute actually for all lambda, right? So that I can tune my weights tune my parameters, in my machine learning application, or so that I can, build a decision support tool to help humans make decisions in a capstone matching example and so forth. Yeah, Kevin.
You make any assumption on function H?
Yeah, I will make assumptions soon on the function H. Yeah. Good. Other questions? Okay. Let me first define a few initial concepts, right? So then when we speak about solving this problem, we're really speaking about determining the solution map or solution path, as I'll refer to it really through most of the talk, right? So what is this? This is just simply the function which maps from the parameters to the optimal solution, right? So it's this function theta star of lambda. And the challenge is, of course, it is computationally expensive to solve all of these problems, right? To enumerate all sets of all possible lambdas, and so we have to somehow deal with that challenge. And the first way that we'll deal with it is relax a little bit the assumption of needing to solve this problem exactly, and speak only about approximate solutions, right? So this is standard, even just single parameter deterministic optimization, for example, at least continuous optimization. Right. So what do we mean? So we define this concept of an epsilon solution path, right, or epsilon solution map, to be some function theta hat, which is a function from the parameter space capital lambda to the decision variables in R to the D, which returns an epsilon approximate solution in objective value gap for all lambda. Right. So theta hat is an epsilon solution path if we have for all lambda in the parameter set that theta hat of lambda is an epsilon suboptimal solution in objective value. Okay, so that'll be our goal, really, to compute epsilon solution paths. And moreover, the key question that we'll address in this talk is like, what is the complexity? What is the computational complexity of computing an epsilon solution path? And how does that depend on epsilon and other problem parameters and so forth? Okay, so the picture that you should have in your mind is a picture like this, and this is really the one-dimensional case and where the name path really comes from. And so in this picture we have, let's say, a single parameter, which as we vary that parameter, it traces out a solution path, right? A path of all solutions here in two-dimensional space. And as we relax the requirement of having an exact solution, then we instead have a band sort of around this epsilon solution path, which the band that defines this epsilon solution path. And so we're looking for points within that band, right? Of course, our results will go beyond just this one-dimensional parameterization, but this is a useful picture. Now, what is the default thing that people do then? So especially in these one-dimensional cases, but perhaps even in higher dimensions, the default approach is discretization, right? So you take your set of maybe continuous values of lambda, and you chop it up into a bunch of discrete points, and you solve the optimization problem at each of those discrete points. And then you use those solutions to somehow construct a solution for any given lambda that you might query, for example, by looking at the closest value in the parameter space or doing some kind of linear interpolation of the points or something like that, right? So discretization is sort of the default approach, and of course the most natural thing that people would think of. My talk, of course, is titled Beyond Discretization, so we want to think about other approaches that may or may not have benefits above discretization. Okay, and in particular, a theme behind our main idea is to leverage global structure of the solution path, right? So discretization, when you think about it, is inherently really a very local procedure, right? So we sort of chop up the parameter space, and then once we do that chopping up of the parameter space, we really just look in a local neighborhood around any given parameter value to determine the nearest discrete point, right? So that really throws away a lot of the global structure of the solution path. For example, in this picture, the solution path has a lot of smoothness to it, right? So somehow that smooth structure is in a large part being thrown away by these kind of local discretization type of methods. Okay, so to summarize our motivating questions, right? Can we develop a method for approximating the solution path for arbitrary parameter spaces lambda? So we do want to go beyond just this simple one-dimensional case. Moreover, in talking about computational complexity, I also want to go beyond just thinking about how discretization works, right? So the classic way of thinking about discretization is your computational black box, right? The building block of your complexity theory is solve a single instance of an optimization problem, right? And then you may ask, okay, how many, optimization problems, how many discrete points do I have to determine to trace out the entire path? We want to go a bit, diving into that black box, for example, by looking at complexity in terms of the number of gradient evaluations, right, or the number of Hessian evaluations, right? So, adopting ideas from, single parameter optimization and the complexity theory of optimization, and extending those to the parameter, the multiple, parametric case. And then finally, in the special case of this, a single dimensional parameterization, where you might have an interval of possible values of lambda, can we better leverage the structure of the solution to develop enhanced algorithms with this ODE perspective? Okay, so then I'll first present this set of results on learning the solution path, which works for an arbitrary parameter space lambda. It turns out that this will converge up to the approximation error level for smooth and strongly convex problems. So those will be my assumptions on H, and we'll be able to analyze the complexity in a more fine-grained way than just the typical approach of discretization, which is to look at only each optimization problem. Instead, we'll dive into each optimization problem and analyze the complexity from the point of view of the gradient oracle complexity. Right. So how many times do you need to call your first-order gradient oracle? And then later in the talk, in the special case of the interval, we'll look at these specialized ODE algorithms, which also can be analyzed in a more fine-grained first and second order oracle complexity sort of manner. Okay, and then I'll show some numerical results. I want to mention before I get to the main part on learning the solution path, some related literature. So there have been several works looking at the complexity of discretization, as I've hinted at. All of these works pretty much just assume that your black box is solving a single instance of an optimization problem. So they want to understand how many single optimization problems do you have to solve to get a good epsilon approximate solution path, right? And so a very nice work along these lines is this Ndiaye et al. 2019 paper, which shows, for example, in the smooth and strongly convex case, that O of 1 over square root of epsilon grid points are needed to actually determine an epsilon solution path in the case of a single continuous parameter lambda, right, the one-dimensional case. Again, in this literature, that's actually also very common. So discretization results beyond one dimension I don't know of any, although it's possible to extend maybe some of the results in that paper, but that paper is focusing on the one-dimensional case. In addition to looking at it from the point of view of discretization, there are also many works on specialized algorithms for problems with special structure. So think lasso regression and related problems, where you can develop a path following algorithm that exploits the special structure of the solution path, right? And in such cases, the path ends up usually being piecewise linear or some other kind of structure like that, and you can develop a specialized algorithm. So that dates back to the early 2000s on lasso, and more recently some variations on the lasso with minimum cut techniques, the fused lasso problem by Dory and her students, for example. And several other examples along those lines. So this is some related literature specifically looking at parametric optimization from sort of a very similar point of view as what we're adopting in this talk. Several other lines of work also have investigated parametric optimization, but perhaps from different perspectives. So, including the work of Pascal and maybe some of you and other people in AI4OPT or former students and so on. So they're looking at this notion of optimization proxies and self-supervised learning, and related to that is also some work on what is called amortized optimization by Brandon Amos, and he has a nice survey paper on that. I think the key distinction here between that line of work and what I'm discussing today, and they're definitely related in a very close way, but often in these works, the primitive is a distribution over the parameters, right? So the basic sort of assumption is that you have an exogenous distribution over the parameters, and you want to learn a good optimization proxy on that distribution, and that's the goal, right? So the goal is to learn on that distribution. Of course, you want to generalize not just to your training data, but beyond your training data, but still there's some notion of a distribution. Here, there's no distribution, actually. I'm going to talk about distributions in a few minutes, but I'm going to construct them, right? So in a way, perhaps, there's a nice way of thinking about the work I'm presenting today, which is it's guidelines for how to think about constructing distributions of parameters in situations where the distribution is not necessarily obvious, right? And there's also a wider scope of literature where distributions on parameters are sort of, again, a key primitive. This includes the work on solvers and integrating learning into solvers, decision-focused learning, and contextual optimization as well. There's a lot of potential connections with that line of work, but again, in that line of work, primarily the assumption is you have some exogenous distribution on parameters, and so that's what I would say the main difference between today's talk and this line of work. All right, that's what I want to say about the related work. Any questions before I move to the learning the solution path? Okay, great. So let me present then this paper and this method. So again, this is our parametric optimization model. So we want to solve for theta star of lambda across all values of lambda, and I'm going to develop some theoretical results. So we do need some assumptions, and in particular, these results are working for convex problems and strongly convex problems that are also smooth. So in particular, I assume H is mu strongly convex and L smooth for all lambda, right? So what that means is that if I look at the first order approximation of the function h for any lambda, and I see a typo here, so there should be a lambda inside of those h's at the bottom inequality. Sorry about that. So for all lambda, you satisfy that the first order approximation is lower and upper bounded by quadratic functions that look like the norm squared between the two different thetas. All right, so standard notion of strong convexity and smoothness in convex optimization. Okay, but the parameter itself is arbitrary again, and there will be no strong assumption made about the parameter space capital lambda. Okay, so here's a roadmap of what I'll do. So our learning the solution path procedure consists of the following sort of four-step recipe. First, we pick a function approximation class. In our case, we'll focus on linear combinations of fixed basis functions, but I'll talk about how that could be expanded as well. Then after you pick the function approximation class, you pick a distribution over the parameters lambda. So again, this is something that we get to choose, right? It's something that we can engineer. You pick those two objects, you sort of glue them together, and then you solve a surrogate stochastic optimization problem, right, that arises after you stick those two pieces together. And you solve that problem, for example, with stochastic gradient descent or atom or whatever optimizer you like. But for our theory, we'll talk about the classic stochastic gradient descent algorithm. This is sort of a roadmap. So let's go through these steps, sort of step by step, right? So the first idea is function approximation. So I've got this epsilon solution path that I'm thinking about, and I want to approximate. I want to build an epsilon solution path, an approximation to the solution path with basis functions, right? That's the idea of approximation. So specifically, assume that I have a collection of p prescribed basis functions. Each of them are functions from the parameter space capital lambda to the decision space r to the d, and we call them phi j for j equals 1 to p. And I can also collect them into a matrix, right? Because I have d decision variables. So I have d rows in this matrix, and I have p different basis functions, so it has p columns. So let's call that matrix of basis functions evaluated at any lambda. We call that phi 1 through p, right, as a function of lambda, right? So I have these basis functions, right? And the idea is that, and sorry, let me also mention that many learning methods sort of boil down to basis functions at the end of the day, right? So polynomial regression, splines, kernels, even neural networks. There you're learning the basis, but at the end of the day, like the last layer of the neural network is really a linear combination of basis functions, right? So in a lot of ways, our results kind of lend themselves to that kind of situation. There are little intricacies to really make it work, but you could think, for example, that these are results that could apply to the last layer of a neural network. Simpler example would be like Legendre polynomial basis, right? So the basis of polynomials up to degree p. Okay. So the idea is we want to build a linear combination of these basis functions and use that linear combination as our approximation to the solution path, right? So specifically, we want to find a coefficient vector beta, beta in r to the p, such that when I multiply beta times this phi matrix, which is just the sum of the beta j's times the basis function columns, that linear operation is an epsilon solution path for all lambda, right? So it's an epsilon suboptimal solution for all lambda in the parameter space. Conveniently, I will express this in an alternative way, which is very simple but convenient, right? So for any vector beta, I can define what I call the solution path error as the worst case supremum error over the parameter set of the difference in objective value between the approximate solution generated by the basis with coefficient vector beta relative to the optimal theta star of lambda, right? So that's the notion of solution path error, right? So it's the worst case error over the space of parameters. And it's a function of your weights on the different basis functions. Right. So so my goal then of finding an epsilon solution path where the approximation function that I'm using is this linear combination of basis functions is equivalently stated as looking for a vector beta of coefficients such that the solution path error, the SP error of beta, is at most epsilon. Right. Moreover, this concept is really useful because now I can minimize this quantity, and I have a notion of best possible solution path error, right? Which is really a notion of approximation error, right? So epsilon star sub SP is the smallest value of this solution path error, and it's an intrinsic lower bound on achievable epsilon, right? So we cannot do any better than epsilon star SP for a fixed basis function class. Okay, great. And so what do we do? So the first thing to note is that, well, okay, I could just say, my optimization problem is, minimize the worst case error, right? So that's like a valid thing theoretically, but we quickly recognize that, we cannot solve that optimization problem, right? We cannot minimize this SP error directly because the evaluation of the SP error depends on this unknown quantity, right? Theta star. It depends on, the problem that you're trying to solve, right? So we're in some kind of circular situation, right? So we've got to circumvent that challenge somehow. And moreover, we want to also, leverage, all of the great engineering effort behind stochastic gradient methods and PyTorch and so on. So we convert the problem to a stochastic optimization problem. Right, we fix a distribution P lambda over the parameter space lambda, and we construct a single stochastic optimization problem, right, that replaces the parametric family of optimization problems, right? And we solve that single stochastic optimization problem over coefficients beta to determine our coefficients and ultimately the approximate solution path. Right. So this leverages the global structure of the solution path, right? Because it brings together a whole bunch of different values of lambda averaged over this distribution, right? Moreover, it's really works for any parameter space, right? So so this could accommodate potentially complicated hyperparameter spaces. You don't need to just have an interval of parameters. And this problem is very generic, so it can be solved with any stochastic optimization method, right? And you can solve it in PyTorch, you can solve it in JAX, however you like. It really lends itself very nicely to those kind of frameworks. Right. So so that's our proposal, right? So we want to solve a problem like this, and so then what we end up with is a problem that's very similar to the problems that are solved in training optimization proxies and in a lot of the existing literature, for example. Question then is for us, like how do we think about the distribution and how do we think about the choice of basis functions, right? And moreover, how do these choices interplay with each other, right? Because now these are two objects that we can engineer, right? We have the ability to think about how to design these objects. So what do we need? Well, really, we need just some distribution such that we can easily sample from that distribution to run stochastic gradient descent. And then we also need basis functions that are easy to compute, right? We want to do fast inference. We want to be able to get quick approximate solutions for all of the good reasons that we want to do that with optimization proxies, for example. So so then question that is natural to ask is how do these choices interplay with each other? And so the first answer to that is that, well, there is a natural condition number, right, induced by these choices. And that condition number is the ratio of these two quantities, right? So given the choice of basis and distribution, we look at the sort of covariance matrix of the basis, but not centered at the mean, but just the the basis matrix transpose itself. We look at that matrix and we look at the eigenvalues of that matrix, right? The spectrum of that matrix, and the largest eigenvalue of that matrix, supremum over the lambda set, so worst case over all lambdas, divided by the smallest eigenvalue of the average matrix, right, the covariance type matrix, is really a condition number of the basis relative to the distribution, right? And this can be seen, with a slight technical result that I'll skip here. For example, because we can ensure that CP, the smaller one, the smallest eigenvalue, is actually positive whenever you satisfy some kind of linear independence assumption. So this is like really, the kind of condition number that is standard for linear regression. For example, the only slight difference here is the numerator is a bit larger than just looking at the expectation, right? Because we're looking at worst case. And we need that to ensure that we can generalize in the theorems that will come, but that's not very restrictive, actually. All right, so this condition number really sort of just intrinsically tells us how the choice of distribution and the choice of basis functions play with each other, right? How do they interact? Okay, and so then the theorem that we can prove now that we have this condition number is the following, right? So consider my sort of surrogate stochastic optimization problem up top, and let beta star average be the optimal solution to that problem. Turns out under these conditions, it will have a unique optimal solution. And then remember, we have this notion of best possible solution path error, right? Epsilon star SP. And for any beta, right, we have the solution path error as a function of beta. So what does our theorem do? Well, it relates the suboptimality of the surrogate stochastic optimization problem to the solution path error, right? Specifically, for any beta, we can bound the worst case solution path error by sum of these two quantities, right? And so we have a way to translate the error in the stochastic optimization problem above to the solution path error, right? And let me parse this a little bit further. So the bound basically decomposes into two different terms, right? One can be interpreted as optimization error. The other can be interpreted as approximation error. Right, so what is the optimization error? It tells you how close you are to the solution of the stochastic optimization problem. Remember, beta star average is the solution to the surrogate stochastic optimization problem. Right, so if you have a good optimizer, you have enough iterations of SGD and so on, you can drive this squared distance to beta star average to be very small. Right, so that error can be controlled by the optimization algorithm. The other term is intrinsic to the choice of basis functions and how those basis functions interact with the distribution. And so that is a notion of approximation error, right? In fact, it's directly proportional to the epsilon star SP, right? The best possible solution path error with a proportionality constant that is the condition number that I had before, right? In fact, it's the condition number of the distribution relative to the condition number of the basis functions relative to the distribution multiplied with the condition number of the functions, right? L divided by mu. So this whole quantity here is really just a condition number of your whole problem, in a sense. And so that approximation error term indicates an implicit trade-off, right? So on the one hand, we can make the basis function class very large. We can have a very expressive model, and correspondingly a very small epsilon star SP, but that might make the condition number part very large, right? That might lead to bad conditioning. On the other hand, we can ensure that condition number is small, but then maybe epsilon star SP will be large, right? And balancing that trade-off, we can do that, and we'll talk about that in a moment. But overall, just the bound in general is nice because it gives us this kind of decomposition and a general recipe for convergence, right? Try and bound both terms, right? Try and make both terms small. Okay, and I want to show now an example of how to do that, right? So how do we bound both of these terms with two example techniques, right? So one is for the optimization error part, how we can bound it in theory using some results on SGD in what is called the near interpolation regime, right? So SGD on problems that are close to this notion of interpolation regime. For the approximation error, we'll focus on a very specific case as an example, which is the case of a polynomial basis, which will rely on some results from function approximation theory. Similar results could perhaps be derived for other choices of basis functions, right? That part is very specific to the basis function choice, though. The first part, the optimization error, is generic, right? So that will work for any basis function. All right, so here's the first part, right? So how can we bound now the optimization error part as a function of the number of iterations of SGD? So consider applying SGD to that surrogate stochastic optimization problem. Turns out that problem is a nice, smooth, strongly convex problem. And so you run SGD with a constant step size, parameterized by some eta bar. And then after t iterations, what do you get? You basically get linear convergence, but you only get linear convergence up to the approximation error, right? So up to this quantity 4CL times eta bar plus 2 times divided by C mu divided times epsilon star, right? So that term on the right-hand side is an unavoidable constant, right? As long as epsilon star SP is positive. But you converge very, very rapidly towards that unavoidable constant, right? The optimization error part can be driven to 0 at a linear rate of convergence. In particular, for any, in the case when epsilon star SP is positive, then as long as your number of iterations is at least some constant times something like the log of 1 over epsilon star, then you can ensure that the overall expected solution path error is proportional to the optimal one, epsilon star SP. All right, so what it says is that, in a nutshell, we converge very rapidly to the approximation error level. And that's exactly what this plot is showing. So these are some numerical results that I'll discuss more in a few minutes. But as a preview, right, what we see here is as we run SGD for more iterations, that's the number of gradient calls or number of iterations of SGD on the x-axis, for different basis function choices corresponding to this Q parameter, which is like the degree of the polynomial. We, at the initial iterations, converge very, very rapidly in terms of solution path error, which is plotted on the y-axis. But then we sort of level off, right? And we sort of level off because of this intrinsic approximation error that is unavoidable. Right? We cannot really, converge down any quicker, any lower than this approximation error. Right? But we reach that approximation error level very, very quickly. So this kind of behavior naturally suggests an adaptive method, right, that iteratively increases the flexibility of the basis function class, right? So you start with maybe a relatively small basis function class. You run a few iterations of SGD, you wait till it stalls, and then you increase the expressivity of the basis function class by adding more basis functions, right? And so that idea is described here in this algorithm, which we call ALSP. Where we iteratively add new basis functions, and then after we add each new basis function, we optimize over the new basis class, or approximately optimize the stochastic optimization problem over that new basis function class, and sort of rinse and repeat until we get a solution, to the desired level of epsilon that we like. Okay, so it's a very natural, idea to not just, run a basis function, model from scratch, but rather to do it in this adaptive way. Okay, about the approximation error part. So here I'll just show the results again that are special for the case of polynomials. So assume now that I'm talking about, for simplicity here, just a single dimensional hyperparameter, but these polynomial results could be extended to higher dimension as well. We'll approximate each component of still though we have multiple components of the decision variables theta. We have d of them. So we approximate each component by a degree at most q polynomial. And so q is the degree of the polynomial, but we have d of these components. So the total number of basis functions is actually q times d, and this basis matrix is some kind of block diagonal matrix. Right. So these details are not so important. The idea is use degree q polynomials, right? Use a polynomial basis. And so there are some nice results from the literature on function approximation that tell us that in such cases, they tell you about the approximation of the polynomial, and we can translate them to approximation in terms of the objective function, which is our epsilon star FP error, right? In terms of the objective function. And in particular, as long as your function is sufficiently smooth, right? In our case, theta star, the actual solution path has some smoothness properties. Namely, nu times differentiable, and these derivatives are having total variation bounded by some constant. Then as long as you pick a degree of the polynomial large enough, right, larger than nu plus 1, you get convergence that such that epsilon star SP goes to 0 as the degree of the polynomial grows, right? In particular, the convergence is like a constant divided by q squared, basically, to the power of nu. And so this bound is going to 0 as the degree of the polynomial grows. That's the important part. And we sort of put all these ingredients together then to get a nice story for this polynomial example, right? Specifically, using the case of Legendre polynomials, which also ensure that the condition number is good, and a uniform distribution over this lambda space, then we can prove that using SGD with our method requires at most p basis functions and at most t gradient evaluations, where the number of basis functions p, for example, in this case of nu times differentiable, is O of 1 over O of epsilon to the 1 over 2 times 1 minus nu, and then the number of iterations gets sort of multiplied with log 1 over epsilon, and also a square there. And in a nutshell, as long as nu is greater than or equal to 3, we beat grid search, right? So we beat the baseline, which is naive grid search, which requires, or rather, I should say, uniform discretization, which requires O of epsilon to the minus 1/2 grid points, and then just logarithmic additional number of gradient calls. As long as nu is greater than or equal to 3, the results in our table here will be better than this discretization. So what does that tell us? It tells us that if the solution path has some structure, right? In this case, the structure is smoothness. You can do better than discretization, right? This sort of makes good sense, right? Because if the parameter space was completely unstructured, right? If you had, just completely arbitrary parameters, beating discretization seems impossible. But as soon as you have a little bit of structure, right? In this case, smoothness, it's one example. Then we can do better than discretization. Okay. And again, this is just what the discretization scheme would do. Let me show some numerical results that also highlight these benefits. Right. So here's a simple, Pascal.
So fundamentally, what you're doing is you replace the min max problem to a min expectation.
Yes.
This is like, what is the mathematical property of the rules?
Oh, very good question. Yeah, it's spot on question. Yeah. So let me go back. So there's nothing. Yeah, it seems counterintuitive, and yeah, let me go here. But you have to remember, what is the bound that we're proving, right? So so the bound that we're proving is that we can have we can replace the solution based on expectation gives you something up to the level of epsilon star SP, right? So it's this best possible one. But that best possible one in general could be very large, right? So this epsilon star SP could be, if you have a very arbitrary parameter space, could be sort of arbitrarily large in a way. But if you have some structure, like in the polynomial example, then you can guarantee this epsilon star SP is small. And so it's like a linear regression problem in a way where, linear regression, even based on 2 data points, as long as you have an actual line, it will extrapolate beyond that. And so all that we're doing here is kind of an extrapolation like that, right? And the degree to which we can perform this extrapolation is dictated by how small this epsilon star SP is. Yeah. Great question. Yeah. Okay, let me show the numerics. So here's a reweighted logistic regression. This is an imbalanced data set, so it's a case where accuracy is the wrong metric, and so we care about false positives and false negatives differently. And so the approach that we will take is to look at a weighted combination of the logistic loss defined separately on each class. So the logistic loss defined on the positive class multiplied with 1 minus lambda plus lambda times the logistic loss defined on the negative class, and then plus a regularization term. And so we want to look at the trade-off between false positives and false negatives. We want to trace out an ROC curve. So to do so, we'll vary lambda between 0 and 1 and visualize that trade-off. And this data set, by the way, has 45 features and 1,000 observations. So we'll compare our learning the solution path ideas using two different basis function classes. So one is the Legendre polynomials that I discussed before, and then we also tried another class of polynomials called Jacobi polynomials with these specific parameters. For the distributions, we use a uniform for the Legendre case, which makes sense according to our theory. And for the Jacobi, it turns out it makes sense to use a beta distribution. The algorithm, again, will just be stochastic gradient descent. Our benchmark is a warm-started version of uniform discretization. So uniformly chop up the grid into different discrete points. And for the number of discretization points, we have a parameter delta, which we vary, right? So we want to explore different levels of discretization, right? How fine are you making that discretization? And so we vary that delta parameter between 2 to the minus 6 and 2 to the minus 18, and then the number of discretization points is chosen as 1 over square root of delta. Think delta is like the approximate accuracy. It's like epsilon, sort of. And it turns out from the theory of discretization, the papers that I had mentioned before, 1 over square root of delta is sort of the right number of points. And then the number of gradient calls within each discrete point, because this is a strongly convex smooth problem, it only needs to be logarithmic. And specifically, we do log of 0.5 divided by delta. All right, so here are the results. So this is the plot I showed before in the case of the Legendre. We can see for different values of Q, right, different degrees of polynomial, we get convergence of our LSP method, right, up to different levels of this approximation error. Right? In particular, the green is the smallest degree polynomial, Q equals 5, so it converges only to about 10 to the minus 3. Y-axis, again, is showing the solution path error. When we increase the degree of the polynomial, Q equals 7, we converge to a smaller degree, a smaller solution path error in red. And then for the largest that we tried here, Q equals 9, we converge to about 10 to the minus 6. The blue shows the uniform discretization, and in particular, as we vary this delta parameter. So how, as a function of gradient calls, though, right? So we have to tweak the reporting here a little bit. So to make things fair, as a function of how many gradient calls in total uniform discretization does, we look at the solution path error that is returned, and we consider this across different values of this delta parameter. And that gives us a curve as well for uniform discretization. And then finally, we have our ALSP, which is the adaptive method. Adaptive method converges very rapidly because it is smartly recognizing when that approximation error has leveled off, and then it introduces a higher degree polynomial. It adds more basis functions. And this allows it to really converge very rapidly. In the case of Legendre, like extremely rapidly. In the case of Jacobi, the results are a bit more neutered in some way, but that's fine. The results also look quite good, right? So basically, similar story in the Jacobi case, although for this example, it just turns out Legendre is a better choice. So yeah, we sort of empirically validate the ideas from our theory with this experiment and see some significant benefits to the ALSP approach. This plot, if you like, shows convergence in the actual space of theta star for a particular choice of the third component. So it shows as you run the number of iterations of SGD, as that increases, you get better convergence towards the true parameters. Here are some results on a multi-dimensional case. So this is a portfolio optimization problem where we trade off the expected return with variance of the portfolio, the risk, as well as a third term, which is a smooth approximation of the L1 norm, right? So this is a sparsity promoting regularization term. And so here we have two parameters, lambda 1 and lambda 2, that are in a box. And we again look at Legendre polynomials with a uniform distribution compared against this warm-started uniform discretization. Here we use LBFGS just to illustrate that we can use a different algorithm than SGD if you like. Results we see here look like this. So For LBFGS, the convergence is a bit different behavior than SGD, but we still see that we're converging to some level of the approximation error, which is a constant for each value of Q, and the adaptive method is able to adapt and increase the basis functions when it recognizes that it has stalled. Here we sort of more dramatically do better than uniform discretization. The reason for that, I think primarily is because we're increasing the dimensionality, right? So even increasing the dimensionality from 1 to 2 just makes discretization harder to scale. And as you get higher and higher, for example, in this next experiment, we have a 12-dimensional case. Scaling discretization just becomes really challenging, right? So and maybe even impossible, right? So so here's an example with again, portfolio optimization, but now we have 12 lambdas. So again, we have a lambda 1, which multiplies the return. We have a lambda 2, which multiplies the variance of the portfolio. And then we have lambda 3 through 12, which you can think of as a reference portfolio, right? So we sort of want to encourage the new portfolio to be close to a reference portfolio. That's what this example is doing. And we use a basis here, which is actually, it turns out this problem is a bit of a toy problem, so you can actually write an optimal solution to this problem. And so as a result, you can actually infer a smart basis from this example. So so this basis, I won't talk about the details, but it emerges from a Taylor series approximation of the optimal solutions here. And so we look at the performance of that basis compared to grid search, like I said, but or no, here actually we just look at our method. We don't look at grid search. Because we're in a 12-dimensional case, we really cannot even evaluate efficiently the worst case error. So so we look instead at a Monte Carlo metric. So we look at the performance on a validation set of size 1000. And on this validation set, we can observe that we do have convergence, right? So we don't really evaluate the SP error here because it's too hard. We just evaluate the performance on this validation set of size 1000 and check that we do get convergence to that set on that set like we expect. And that's what we see in these plots. Right, so in a way, this is sort of just a demonstration that our method is scalable to higher dimensional cases. And moreover, I think this example illustrates another case where the structure of the optimization problem actually informs the choice of basis, and then subsequently, why you're actually able to learn anything here, right? So we use a basis that's informed by the structure of the optimization problem, actually. It's informed by the solutions of the problem. And so once again, it's like in general with arbitrary lambda, we don't expect to always be able to learn. But if you use a smart basis, then and your problem has some structure, then you have some hope, right? And this illustrates that idea. Okay, I don't have time to talk about the ODE perspective, but I just want to mention that in the specialized case of a single parameter here, the notation is changing because of this is a different paper. So to be consistent with that paper, we use X for the solutions. And in the case of a single parameter, we can derive an ODE, it turns out. And this ODE also offers an alternative way to think beyond discretization by applying numerical methods to this ODE. Right? So the ODE characterizes exactly the solution path in the one-dimensional case. And you trace out approximate solutions to that ODE by using your favorite numerical method. For example, Euler's method here in this algorithm, or a trapezoid update scheme, or Runge-Kutta update scheme, and different types of interpolation and so on. You can exploit all of these tools from numerical analysis with ODEs and apply them to parametric problems with a single hyperparameter. Of course, when you talk about multiple hyperparameters, right, then the ODE is no longer an ODE, right? It would be some kind of partial differential equation, and things would become more difficult, right? So this is very specialized for the one-dimensional case. But nevertheless, in that one-dimensional case, which is important when you have things like regularization, for example, you're able to get really efficient algorithms. And we improve convergence bounds on these numerical methods. Okay, so in conclusion, this talk demonstrates some ideas about how to go beyond discretization and parametric optimization, in particular in cases where you really need to solve the parametric optimization problem for all values of the parameters. Some of the themes that we saw were that to be able to effectively do this, especially when you have high dimensionality of the parameter space, you need some kind of underlying structure of the solutions. For example, smoothness, which allows the polynomials to learn, or some other structure. In general, though, this methodology, I think, is really nice because it offers a great degree of flexibility. You can choose any basis functions or really any function approximation scheme that you like, and you can leverage existing software to run SGD. Future work would include a more careful examination of non-parametric methods like deep neural networks or forests of boosted trees, going beyond just the fixed basis functions. And then we also saw for the briefly for the case of a single parameter, the ODE perspective can improve things even more. I think there are many exciting directions regarding parametric optimization and AI. And Weam has been working on some of these as well, and she'll I think chat with some of you later this week about that and maybe give a presentation as well. And so that's not today, but hopefully you can talk with her. Okay, these are the two papers that the talk is based on, and thanks everyone for your attention. Happy to take any more questions. Yeah, Kevin.
I think the first question. Still amazed that you picked one distribution and then it works out. Did you see any practical value of updating the distribution?
Great question. Yeah. This is like 2 papers from now. I really see this as a great direction as well. Yeah. Yes. And I think there's a lot of potential there. So because intuitively we want to sort of fine tune the distribution in a way where it's adapting to those lambdas which are most difficult, right? The ones that are really like if you can solve it on those, the sort of optimal discretization in a way, right? And so it's really natural idea to think, not just have a single distribution that you fix from the start, but rather update that somehow over time by some other kind of learning method that's put on top of this. So I think it's a great direction. Yeah. Thanks. Yes.
Top of that, so how do you construct the distribution right now? It's based on some prior knowledge, or?
It's a great question. Yeah, it's sort of right now we're doing the distribution in a really ad hoc way, so it's based on prior knowledge for specific problems. Yeah. Basically, according to our theory, we have to guarantee that this condition number is small, right? We cannot have the condition number blow up too much. How to guarantee that? We only know how to do it in an ad hoc way right now.
Okay, last chance for questions. Okay, let's thank our speaker one more time.